Okay. Share my screen. Okay, share screen. Okay, can you all see my screen? Can I get an answer from someone?
Yes.
Yes, we can see the screen.
Okay, thank you. So, okay, so these are some of the great answers you gave. So alveolar opening is supported by compliance. Elasticity of chest wall promotes alveolar opening. So this is true. So having some opening, so you need a certain elasticity to the chest wall to allow for opening, right? So it's pulling on it. The elasticity of the lungs also promote closing too, right? So also promote kind of returning back. And so it depends on the part of the breathing cycle. But these are all good. So surface tension promotes collapse, intrapulmonary pressure. So someone put intrapulmonary pressure. So could that person or somebody kind of maybe clarify that? How does intrapulmonary pressure, what does it need to be at to promote opening or closing?
Hey, Chris, just a heads up. I think
Yeah.
there's only 13 of us in here, so I don't think everybody's back in yet.
Oh, okay. Sad. What a mess. It's so annoying because I actually have I have a paid subscription. I just must have not logged in using it. Okay, does anybody want to qualify that statement there about alveolar opening?
Can you repeat what the person wrote?
Yeah, so the person had wrote here, intrapulmonary pressure promotes opening, and I'm just wondering, like, in what sense that is.
I didn't write that, but would a decrease in intrapulmonary?
Yeah, decrease in intrapulmonary pressure would promote opening. Yeah, I don't know if that's what you were finishing, but I feel like that's what you were saying at the end. Is that right? Yeah. Okay. Yeah.
Chris,
so
is this fixed?
What's that?
Is this fixed?
What?
The new meeting.
Yeah, this is the new meeting. I don't know. I just opened it again. I sent an invite to everybody again.
Okay.
So yeah, I'll have to figure this out because I have a paid subscription, but for some reason it doesn't know that. I don't know why. And so when I tried to pay, it said I have a paid subscription, but then it cut me off. Dawn made it. So if Dawn was able to figure it out, I think most people would be able to.
Got him.
Okay. So I think that's an important thing to consider, like what factors promote opening, what factors promote collapse, to think about kind of a big picture view on the lung in that perspective. Okay, so can everybody see my screen here, the pulmonary circulation?
Yeah.
Yes?
Yes.
Yep.
Yeah, okay. All right, so this was an important piece. So blood flow can be pretty varied across the lung. And so this is where I said in class that stuff would be a little bit more different when thinking about, this would be a new topic for us, I guess, with respect to breathing. So it's important, right, to realize that blood flow varies across the lung. So blood flow is actually the least at the top of the lung, where gravity, where there's not a lot of molecules kind of piling, I think is one way of thinking about it. And then at the bottom of the lung, the blood flow is greatest. And then blood flow is greater in exercise than at rest. Okay, so let's look at some of this. There are these three zones that you need to think about with respect to the lung, zones 1, 2, and 3. There's a really great explanation about how pulmonary circulation and blood flow changes on pages 511 and 12. Zones 1, 2, and 3 vary basically by the height in the lungs. And so if you look at this second diagram here, zone 1 areas are more or less at the top, and zone 3 areas are more or less at the bottom. Let me just kind of describe what's going on here. So the idea here is that we're looking at pulmonary arteries and pulmonary veins. So arteries are where the blood comes in to a capillary bed, and then the veins take the blood out. It's acknowledged here that these alveoli sit around these capillaries, and that the alveoli can exert a pressure on the capillaries themselves. In a zone 1 situation, the alveolar pressure can be so great that the blood flow actually stops or is not allowed to persist in a zone 1. So the idea is that in zone 1, you'd have pressure coming through in this point, but the alveolar pressure would be so great that it'd be essentially closing this off or shutting the door so this blood can't come through. So zone 1 situations are not normal, and they only happen in kind of like disease states. So, or in other states that are not typical. So one really great example of where you can have a zone 1 situation persist is in the case of positive pressure. So we've been looking or thinking about these particular people that are on respirators all over the world with this COVID-19. One way that we're keeping them alive is we are forcing air onto them, right? We're forcing their lungs open. Imagine these people have pneumonia, or they have a lot of fluid in the lungs, right? Maybe I'll talk about this another time, but if you have pneumonia, that's a fluid buildup here, so there's a lot of back pressure, making it hard for them to get any air into these spaces. With positive pressure therapy, you push on the alveoli to basically force the lungs open and push air into these spaces. Of course, with that though, you can collapse the circulation and not have a lot of blood flow through. So while you need the positive pressure therapy to provide the air, there's also this drawback to snapping the lungs shut, if that makes sense. So zone 1 is an abnormal situation. Zone 2 and 3 happen in the lungs. Zone 2 is a situation where the pulmonary circulation varies depending on the cardiac cycle. So in the systolic phase of the cardiac pumping, the arteries would have a high pressure, and so chances are you can push through that capillary bed. In the diastolic phase, in some areas, you don't have enough pressure to kind of push through. So the concept here is that the amount of flow will be dependent on the state. In zone 3, the circulation's always open because of the fact that in these zones, you'll have enough kind of gravity forces or sort of molecular piling, I think is another way of thinking about it, that you can actually push through because your pressure is so great in that particular area. So zones 2 and 3 are what is typical in humans, at rest and also in exercising. So it's also interesting to notice that you can vary between zones. So like one part of the lung might be zone 2, but then when you're exercising a lot or your heart's pumping a lot, you can convert that zone 2 to a zone 3 because the pressure from the heart will be so much greater. And so you have this kind of always open. So even during like the diastolic phase, you wouldn't necessarily be snapping that area shut, if that makes sense. So here's a look at this. So this is zone 1 up here. So in these cases, you have a positive pressure coming from breathing in all of these cases. In zone 1, you can cut that circulation almost off completely. In zone 2, the amount of blood going through will vary depending on whether you're at the systolic or diastolic phase. And then in zone 3, it's kind of always open. So take a minute now and think about what the effect would be on lying down. How would lying down affect what zones exist within the lungs vis-a-vis zones 1, 2, and 3? So take a minute and think a little bit about that. And then we'll talk about it together. And I think there's a requirement for this in your assignment or somewhere. Okay, so what do you expect happens with lying down? Does anyone want to share?
Yeah, I'd guess that zone one wouldn't have the like difference in pressure, and it would look more like, or maybe zone one would be up to the top of the chest if you're laying on your back, um, and it would kind of flip, but there'd be less weight of all the blood on all the areas, so there'd be less pressure throughout the system.
Yeah, yeah. You mentioned weight. So I like to sort of think of this as a little bit like a sort of going up to high elevations, right, and air molecules, if that's helpful. So like if we're at sea level here, we're experiencing a lot of air molecules above us, right, and those are kind of weighing us down. When you move up a mountain, there's less air molecules or less pressure. So at the top of the lungs, there's a gravity force that the heart has to overcome, and so the pressure is very low at these positions. When you lie down, no part of the lung is significantly higher than the heart from a blood perspective, and so you convert some of these zone 1s into zone 2s, zone 3s at the same time into zone 2s. So you sort of equalize or normalize the circulation along the lung. So from a blood pulmonary circuit perspective, it's better to lie down from that perspective, but there are other negative aspects to like lying down. But yeah, that's the idea. So lying down, and again, you can read this all in 5.11 and 12. So lying down will minimize those gravity effects. The other thing that's important to think about is exercise. So exercise has this job of increasing the amount of cardiac output, so that you're sort of increasing the number of zone 2s and 3s kind of thing in the lung. Okay. All right. So the last bit here related to the lecture is looking at 16. So in 16, we spent some time, if you haven't looked at it yet, you'll look at it tonight or tomorrow. In 16, we're starting to look at those factors that control our breathing. So one really important diagram is this one. This one shows how peripheral and central chemoreceptors contribute to the respiration and the respiratory rate. So basically, when you're when you're using oxygen, your oxygen levels will go low in your body, and your CO2 levels will go up, and your pH will go down, or otherwise your hydrogen ion concentrations will go up. If your plasma CO2 levels go up or your pH goes down, there are structures in the body that can detect that. For example, there are these aortic bodies and carotid bodies. Those are the ones we looked at with baroreceptors. These guys are able to detect that decrease in pH and signal to the medulla to increase respiration or ventilation, and that would in effect increase blood pH. Plasma CO2 increases can be translated into a decrease in pH in the interstitial fluid, and those signal to central chemoreceptors in the same way to trigger the respiratory centers in the medulla to increase respiration. Okay, I'll be right there, okay? Okay. By the way, guys, it's time for the marshmallow challenge, just so you know. Okay, so one important piece here to consider, and I hope I've emphasized this well enough, that CO2 levels are used to detect oxygen requirements in the body rather than O2. So what you should be seeing here is like the total minute volume on the left is a reflection of like how many liters per minute this particular individual is respirating at or breathing at. As we vary their CO2 or vary their O2. You can see that the body's really responsive to changes in CO2, but it's only when the O2 levels get pretty low that the body actually becomes responsive to the O2 changes. So the idea there is that the body uses CO2 as a measure over O2, and it actually makes a lot of sense because the structures in the body that are detecting CO2 and O2 are structures that are found bathed in fluid, be it interstitial fluid or plasma. And so they need to be detecting something that's in fluid. And oxygen, frankly, is just not really dissolved that much in plasma. There's a little bit in there, but the amount of oxygen in that space is so little that it doesn't make sense to use it as a great marker of what the body's needs are. And that's because most of the oxygen is found on hemoglobin. And so if you look at this curve, this is a saturation curve that examines the percent saturation of hemoglobin with respect to oxygen concentrations. And so you can see here that even like a dramatic decrease in oxygen concentration in a system, say from 100 millimeters of mercury to 60 millimeters of mercury, which is a 40% drop, doesn't actually mean that the total availability of oxygen is substantially different, right? You only have a 10% drop in oxygen availability, even though there's been a 40% drop in oxygen concentration. So throughout evolution, I suppose, the idea there is that it doesn't make sense to rely on oxygen concentration as a very good kind of measure. Okay, so that's kind of one big take-home point. The next thing I think that's really important for us to do is to consider these oxygen hemoglobin dissociation curves and what affects them. And the important kind of piece here is that deoxyhemoglobin, and I'm just going to stay a little bit beyond the time. If people have to leave, you're welcome to leave. I'll keep the recording going. But the idea here is that with these hemoglobin, oxygen hemoglobin dissociation curves, we can keep track of whether oxygen is in a loaded state or it's on top, it's on the hemoglobin, or if it's unloaded and off of the hemoglobin. So there are two basic reactions that are important. There's a loading reaction where deoxyhemoglobin is converted into oxyhemoglobin. And then there's a conversion of oxyhemoglobin to deoxyhemoglobin, which is an unloading reaction. And so the degree to which you would observe loading or unloading in a given tissue is essentially dependent on one of two things: the oxygen concentration of the environment on the one hand, and then the affinity or bond strength between the hemoglobin and the oxygen on the other. Okay, so let's look first at this graph. So this graph is showing us the percent saturation of hemoglobin, again, in different oxygen environments. So what you can see is that oxygen is all loaded or on the hemoglobin when the concentration of the environment is high. And so this would be where the lungs would be up here. As you decrease the oxygen concentration of your environment, the percentage of saturation decreases, like we mentioned a moment ago. So the relationship here is that the partial pressure of oxygen of the environment matters, right? If you have a low partial pressure of oxygen, you promote unloading. And so that's just basically a statement that the oxygen is unloaded to its environment if the environment needs it, right? Another interesting kind of point to realize is that most of our oxygen actually remains on our red blood cells, and we don't completely often deplete it, right? So for example, these are the arteries in the body. These are where you have fully oxygenated blood leaving the heart. And so here you have 100% oxygenation. Over here are the veins at rest at 40%. You can see that you basically oscillate between 100 and 80%. You don't often dip down into these lower areas. And so again, for that reason, it doesn't make sense to use oxygen levels in the body as a really good measure of what the needs are. Only in people where the oxygen levels get surprisingly or exceedingly low does it become relevant, and that those people are experiencing hypoxic drive, which is in your, which is what we discussed a little bit in that lecture. Okay, so I want to just quickly kind of go over this effect of shifting the curves to the right. Okay, so the idea here is that if you decrease pH or increase temperature or increase 2,3 BPG, you shift the deoxyhemoglobin, the saturation curve to the right, okay? So here, for example, is pH 7.6, 7.4, and 7.2. As the pH decreases, we shift our curve in this direction, and the thinking there, the truth there, is that by changing the pH, we promote unloading. So if we look at the same partial pressure concentration here, keeping PO2 fixed, we in effect can see that we can unload more. So at like 45, for example, we're at like 85%, but at 7.4 at 45, we're at 75%, and then 7.2 at 45, we're over at 65%. So decreasing pH increases unloading, and the reason is a chemical reason, right? So as you have an increase in hydrogen in the cell, in the red blood cells associated with the hemoglobin, the degree of the chemical reaction promotes a state that unloads or releases the oxygen in that environment. So that's the case for temperature, pH, and also for this 2,3-BPG. So I explained in the lecture, 2,3-BPG is something that's produced in the context of increased glycolysis, and that tends to shift the curve to the right. Okay, so take a minute and think about this question. So this question is showing red and green curves, and the question asks, which of the above oxygen hemoglobin dissociation curves corresponds to blood during resting conditions, red line, and blood during exercise, or green line? So take a minute and think about that. Which one do you think would be green, or would be exercise, sorry?
B.
Okay, somebody says B, great. Okay, so let me go through the answer here. So in some of these green ones here and here, there is for some reason, decreased saturation in the presence of maximal oxygen levels. And so these ones don't really make sense in the context of a normal person. The implication in these two is that there's something wrong with the loading function of the hemoglobin. Perhaps they have anemia or something like that. So the best ones are these options over here. Someone said B, it sounded like Don's voice to me. B is the right, maybe I'm wrong. Was that you, Don? No.
Nope.
Okay, sorry. All right, so B is the correct answer, and you can look here. In exercise, several factors shift the oxygen hemoglobin curve to the right. And this all serves to deliver extra amounts of O2 to the exercising muscle fiber. These factors include increased quantities of CO2, which I didn't mention here, but is in the lecture. If you increase CO2, you push the curve to the right. So increased CO2 released from muscles would shift the curve. Increasing H plus because of the increase in CO2 would shift the curve to the right. Increase in temperature from the heat generated by exercising muscle would also shift the curve to the right. All of these result in more oxygen being delivered in a given amount of time than would normally be the case, okay? So when you're exercising, there are some cool things happening, right, from a respiratory physiology perspective. There is this increase towards unloading. There's also a move towards more of a zone 3 kind of thing, right, inside the lungs. There's also, you know, these kinds of effects of having increased CO2, increased blood, decreased blood pH. This would trigger respiratory centers in the brain to increase ventilation. So if you can kind of see those big picture pieces, I think that's really helpful when thinking through some of this. Okay, let's go quickly. We're a little bit over, but for those of you who are sticking around, let's do a couple more poll questions here. So if you could go to pollev.com and I will put up some questions for you here. And feel free to click on this question where the lungs are found on the oxyhemoglobin dissociation curve below. Great. So a lot of you are choosing the top part correctly, so that's where the lungs are found. So the lungs have a lot of oxygen here, and that's at partial pressure of 100, or depending on the constant environment that you're in, and you would be loading. So this represents percent hemoglobin saturation. So it's like how much of the red blood cells are actually saturated with oxygen. As you move towards lower and lower concentrations of oxygen in the body where there's metabolic processes happening, you can dump that oxygen off, right? And so then you'd be getting to kind of down here, and that would be more like capillaries and veins. So the answer to this comes from an appreciation of this material here, where the veins are at rest, and then these are the lungs up in that location. Of course, it would, I guess, depend a little bit on where in the lungs, right? So maybe a better thing would be to say at the, you know, the arteries leaving the heart. Maybe be a bit of a better answer. Okay, so let's clear responses. All right, activate. Okay, so click on the oxyhemoglobin curve below with the lowest PCO2, lowest partial pressure of carbon dioxide. Okay, so just like pH shifts your curve to the right, high CO2 shifts your curve to the right. In this question, it's asking you which would have the lowest PCO2. So the lowest PCO2 means you don't need to unload very much. So for example, in these curves, if you keep the partial pressure of oxygen at 40, the one that has the most loading is curve A. That's the most loaded, or the least unloading, right, would be curve A. So this one represents the one that would be mostly loaded. So the answer is A. If we increase the CO2 levels, we shift the curve to the right, and this would be the highest over here. So the correct answer is A. All right, so which patient might have acidosis? Okay. Okay, great. So the answer is C for the same reasons as we mentioned before. So that's the Bohr effect. Great. And then which one would have the highest fever? Okay, I think you guys got this. Excellent. So F would be the highest fever. So tell me a little bit about, let's just stop for a sec here. Tell me a little bit about these patients with this COVID-19 then. What would they be from a perspective of a graph like this, or these hemoglobin curves? What would be happening with them? Anybody want to share?
Would it be that the increased temperature, well, it's just the curve to the right, and then the increased temperature also increases the pH, which increases the CO2, which decreases the O2? Okay,
yeah, so everything, Yamaya, shifts to the right. So increased temperature, increased CO2, and decreased pH or increased H+, those all shifted to the right. So the temperature doesn't necessarily change the CO2 though. So like you don't have to draw those two things together. So it's like that's separate. So I would say these people have a high fever, right? Because they have an inflammatory response happening. So that would promote unloading. They also would have like probably really low oxygen environments in their body, right? Because they're not getting the air that they need. Because of the lung infection. So that would promote unloading. So their bodies would be working hard to kind of get this stuff into their body as best they can. So I would say that their curves would be shifted to the right big time compared to most.
Sorry, That's my dogs. They
That's
have a
cute. Sounds like a baby.
Ah,
Okay.
Um,
Let's do a couple of Yeah. Did somebody have a question, Heidi? Go ahead.
yeah, quick question on that curve. Would it also be shorter, as in not reach 100% saturation?
Interesting. That's something to look at. Like that, those curves are examples of anemia. So yeah, it could also be. I'll look that up actually because right, if they have decreased oxygen transfer in the lungs, the degree of loading could be very low, right? Is that what you're getting at?
Yes, like just, I guess, if they've got all that congestion or
Yeah.
they can't do the gas exchange, would it be below 100% saturation?
Right. Totally. Yeah, I'd love to look that up before I get back to you, but let me. That seems reasonable, right?
Thanks, Chris.
Yeah. Okay, let's do a couple of random questions here. These are from the blood time. So let's do some of these for those of you who are still around. So these are from the blood. So which plasma protein is accurately described? You guys still here? Okay. Okay, people are liking B.
Hey, Chris, I got a quick question.
Sure.
How do we access the recorded lecture?
Like this thing?
Yes.
I'll put it on Moodle.
Cool. Thank you.
Yep. All right, great. Yeah, answer is B for this. The other ones don't work. So beta globulins, fibrinogens involved in clotting in A. Alpha globulins are also involved in transport. Gamma globulins are also known as antibodies. And albumins are involved in the hypertonicity of the blood for osmotic pressure. Which of the following are most active as phagocytes? This is good. Looks like Jeff finally did something of value, teaching you guys about neutrophils. That's great. And neutrophils are very phagocytic. Awesome. The basic event that's involved in the formation of a blood clot is the change of so great. Fibrinogen is the monomer and fibrin is the polymer. So basically we're trying to produce a fibrin mesh. Activate. Okay, so here's a chance for you to put in a little answer to what is meant by a serine protease and how is it involved in hemostasis? I asked you to know about not everything from the clotting cascade, but to know the function of a serine protease and the function of a transglutaminase. I got one answer so far. Breaks proteins at a serine residue. Activates by cleaving. Yeah, breaks bonds, cuts serine groups. Yeah, these are great. So proteases cut proteins. In this case, they cut at a serine. So whenever you go from like factor 10 to factor 10 activated, etc., that happens because another factor cleaves an inhibitory domain off of that factor to make an activated version. So it kind of looks through and cleaves these serines off, or not, at serine positions to kind of produce an active form. That's great. All right, what's a transglutaminase? Is she not here? Yeah. Okay, so transglutaminases, they do promote clotting, but more specifically, they link glutamines. So what they'll do is they'll find neighboring glutamines and they'll stick them together. And this allows for laminating or linking of fibrin molecules, which is an important process in making all these things link up. Okay, so, all right, and we talked about this already. Okay, so today we've done a little bit of review of the lectures. I'm going to post a little mini video on why the intrapleural space is always less than the intrapulmonary space, and Sindra explained it well with the pulling of the chest wall out and the pulling of the lungs in, the elasticity parts. And we'll be in touch. So on Friday, we're going to have a more or less normal maybe lecture on organization of the nervous system. And I may try to post some things ahead of that. For the most part, though, these Zoom meetings are supposed to be chances for us to kind of go over some big material and answer some talk through some questions together. Also, if you have questions for me or would like to have an office hour, I know that some of you were doing that really regularly before. Please contact me so we can do that again. I think it's a really important piece. And that's it for now. Unless anybody has any questions. I think the more we do this, the more things feel normal and get on track. Any question before we go? Okay, great. Well, have an awesome day. I'll post these videos and I'll be in touch. Take care of yourselves and each other, I suppose, too.
See you, Chris.
See you guys. Take care. See if I can figure out how to turn this off now.